The next series of videos we're going to be looking at vectors. So before we make a start on that, we just need to make sure that our basic skills are up to scratch. So this video will just address a few of the key skills. First of all, we just need to make sure we understand the difference between a vector and a scalar quantity, and that is essentially that a vector quantity has both size, which we'll term magnitude, and direction in comparison to a scalar quantity which just has direction. And the classic comparisons are speed, which tells us how fast we're going in terms of the size, but doesn't give us the direction. If we also want the direction, then we will be talking about velocity. So if I started at this point here, walked north for 4 kilometers and east for 3 kilometers, I would end up here. My total distance would have been 7 kilometers. However, my displacement would mean I am 5 kilometers away from my start point here. In terms of expressing vectors, we should be happy with these three ways. Here, I'm expressing as a column vector. Here, I'm just expressing as vector AB, and I could also term this vector A, which is emboldened. If I was writing this out by hand, I would just write a squiggly line underneath it. The way that is probably new to you is this here. So here we're looking at unit vector form. So the logic should be fairly easy to interpret. Essentially, I and j are going to be our x and y coordinates, and we could express these using the unit vectors I and j, which are called base vectors. We can take it also into 3 dimensions using a k vector. So the k is going to be the z direction, so this would be the 3rd dimension. So if we have a look at these individually, if I was to have a unit vector in the x-axis, so if this is the x-axis and I had a unit vector of length 1 here, then I'm going across 1 in the x direction using the unit vector I. So I'd have a 1 in this here, in this position here. I'm not going into the page, so this would be 0, and I'm not going up, so this would also be 0. So the unit vector in the x direction I would represent like this. So I would say I equals 1, 0, 0. The unit vector in the j direction, similarly, I'm not going across, so that's 0. I'm going 1 into the page in the direction j, so that's 1, and then I'm not going up. So the unit vector j is 0, 1, 0. And similarly, the unit vector in the z direction would be 0, because I'm not going across, so I'm not going into the page, I'm only going up 1, so that would be 0, 0, 1. So we can use these base vectors here to express vectors as well. So just to check your understanding of 3 dimensions, I suggest you just confirm that you agree with the coordinates for each of these points. So if you look at the information here about this cuboid, you should be able to reconcile this information with the coordinates of these points here. Magnitude of a vector then, fairly straightforward. We use the modulus symbols to denote what we are interested in in finding. So this is the magnitude of vector AB, and we find it using Pythagoras. So this should be, as I say, fairly straightforward. Again, the only thing here possibly is this terminology. You would have seen this format before, but we can also use this to express the vector. So consequently, the magnitude will be found using Pythagoras. And if we're working in 3 dimensions, we're just going to extend the formula. So very quickly then, just have a go at a few of these questions here. Find the magnitude of each of these vectors. So the solutions then, this is going to be root 25, which is 5. This is going to be root 10. This is going to be root 9, which is 3. And this is going to be root 49, which is 7. And this is going to be root 2. So that's just substituting these into Pythagoras' formula. Some of the language and key concepts then of equal, negative, and parallel vectors. The key thing to remember is they will only be equal if they have both the same magnitude and direction. So these two have the same direction, we can check that using the gradient. They have the same magnitude, we can check that using Pythagoras, so we can confirm they are the same. In this instance, whilst they have the same magnitude, they are in the opposite direction. So they are not the same vectors. In fact, however, if we look at the column vectors, we can see that this is the negative of this. So this would mn would be termed the negative vector, and we could say that AB equals negative mn, or vice versa. In terms of parallel vectors, if they have the same direction, these vectors, then they are parallel, even though the magnitude is not the same. And we can say that more generally, two vectors are parallel if one is a scalar multiple of the other. So if we have any two vectors here, if one of them is a scalar multiple of the other, they are parallel. And if we take vector AB here, we can see that it is half of vector CD and twice of vector EF. We can see that in this instance, AB is a scalar multiple of CD, AB is a multiple of EF, scalar multiple of EF, therefore they are parallel. So for this question, write or express each of these vectors in terms of vector A, and then there's a challenging question here. For what values of t and s are these two vectors parallel? So if we've got vector m equals 3i plus tj minus 6k, and vector n equals 9i minus 12j plus sk, for what values of t and s are these vectors parallel? So this is the column vector for each of these, and we should be able to see that vector b is half of the magnitude and in the opposite direction. Vector c is twice the magnitude in the opposite direction. Vector d is the same magnitude as a in the opposite direction, and vector e is twice the magnitude in the same direction. So the extension, this was a little bit harder. We need to understand that if they are parallel, so here we are assuming they are parallel, vector m will be a scalar multiple of vector n. So this is vector m, we're told here, so it must be some scalar multiple of vector n. So we can expand this and we end up with this formula, in which case they must be the same, must be a scalar multiple. So we can set here 3 equal to 9k, and that enables us to solve for k, so k must be a third. Now we've got two unknowns, so if we look at t, we can say t must be equal to negative 12k. Fortunately, we've solved for k, so we can see t equals negative 12 times a third, which equals negative 4. So t would have to be negative 4. Similarly, if we're looking at k, negative 6 must be equal to s times small k. So therefore, we know that k is a third, so we can solve for s by dividing negative 6 by a third and getting negative 18. Position vectors then, so this is just the position of a vector relative to the origin. So here I've got a vector at the position negative 5, 12 relative to the origin. And I can also express that using unit vectors I and j. Finally then, the resultant vectors. Can you find two ways to represent vector A, B? In the first instance then, we need to look at the position vector. So position vector of A will be from the origin I go across 2 and up 3. The position vector of B I go across 6 and up 6, so that'll be 6, 6. It should be fairly intuitive then for you to see that vector AB, if I'm starting it here and going here, I need to go across 4 and up 3. However, we're going to try and generalize that. So if I want vector AB, one way I can do that is by going from A to O, and then from O to B. So that's what I've said here. Vector AB is the same as vector A to O plus O to B, which should be fairly straightforward. Vector AO here is the same as the negative of OA. So I can take this and substitute it in here, which yields me with vector AB is the same as negative OA plus OB. I can rewrite this then as OB minus OA. Why is that significant? Well, in this instance then, we can say that the resultant vector AB is the result of subtracting the position vector of A from the position vector of B. So this is the key result to take away, and we can apply that to find the resultant vector more simply. Points A and B have been given the coordinates negative 3, 2, 0, and negative 4, 7, 5. And we're asked to find the resultant vector of AB. So let's try and use this result to try and have a go at finding the resultant vector. So first thing I would do is encourage you to plot a sketch. We've got the coordinates, so we can write down the position vectors of OA and OB. That's just interpreting this information and putting it in column form. And use the result previously that the resultant vector AB results from subtracting the position vector of A from the position vector of B, and if we do that, we can see that we will end up with a resultant vector of negative 1, 5, 5. So we've looked then at how we can find the resultant vector using the position vector. So if I have here vector AB, I can find the resultant vector by subtracting the position vector A from the position vector of B. Now we can generalize this. It doesn't have to be just the position vector. We can actually use this principle whenever we have vectors expressed relative to a constant position. So for instance here, if we have vector PQ and we have vector PR, so we have both of these vectors expressed relative to the same point. So if that's the case, then we can actually find out the resultant using a similar approach. So if we wanted to find the resultant QR, so we've been given PQ, we've been given PR, we want to find the resultant. We can express it in the same way by saying that the resultant vector will be our second vector here, PR, minus our first vector here. So if we look at it diagrammatically, we should be able to see that vector QR would be QP plus PR, and QP is the same as negative PQ, so we would end up with here our second vector relative to P, so PR, minus our first vector relative to P, so minus PQ. So let's just have a look at this question together then. Given that vector xy has in component form is 2, 1, negative 3, and vector xz in component form is 0, negative 10, negative 1, find the vectors yz and zy. So it might help just in terms of thinking about it to replace these letters with x, y, z. So just have a go at that yourself, and then we'll try and go through it together. So in this instance, we're asked to find the resultant vector yz, which would be this vector here. We've been given vector xy, which is this vector, and xz, which is this vector. So we should be able to see that the resultant vector yz would be yx plus xz. So yx is the same as negative xy. So we would end up with xz, which we've got, minus xy, which we've got. So the resultant, therefore, would be 0 minus 10 minus 1 minus 2, 1, negative 3, which is xy. And if we do that, we end up with negative 2, negative 11, and 2. Part B then, not quite as hard as it looks. We're being asked to find zy. Now we should be able to recognize that zy is going to be the same as negative yz. Now we've already found in part A what yz is. So all we need to do is take the negative of our answer in part A, and then that will give us vector zy, which is just going to be 2, 11, negative 2.